So, good morning again, everyone. Today is our last day, but we have two presentations more, and they're not only important, but I'm quite sure very interesting. And the first lecture will be given by Andrei Shiryaev, who is expert in analytical spectroscopic techniques to work with the nuclear materials of different kind, I would say. So, Andrei, please.
Yeah, thank you for the introduction. I don't know if you can hear me. Hopefully, yes. So I will speak mostly about characterization of spent nuclear fuel and materials which resulted from nuclear accidents. As far as I understood yesterday, yeah. As far as I understood, last week you have heard something about materials which were produced during Chernobyl accident, but I will speak mostly about the results of results of investigation of behavior of nuclear fuel during the accident and afterwards. So just a brief reminder, of course, you know this already from this school, and most likely you knew it before. So commonly, the fuel in modern power reactors is made from sintered uranium dioxide, even sometimes mix it with plutonium dioxide, making MOX fuel, with relatively moderate enrichment in uranium-235, which is now reaching something like 4.5% or some slightly higher. So in the beginning of the nuclear era, the enrichment was usually lower, something like 2%. And for example, in Chernobyl reactor, the enrichment was close to 2.4%. Enrichment in uranium-235 to 35. So, as you know, fuel pellets are encased in hermetically sealed tubes made from zircaloy or zirconium-based alloys. Actually, the name zircaloy comes from zirconium alloy. And then several rods are combined into fuel bundles. So here you see an example of a fuel bundle from RBMK reactor or Chernobyl type reactor. Here you see some examples of other types of fuel bundles, for example, for VVR. And just to understand the scale that you see that, for example, in a large RBMK type reactor, like was in Chernobyl, for example, the number of fuel bundles was quite significant. The core of the reactor was fairly large. Now, nowadays, in VVR type reactors, the core is somewhat smaller, but nevertheless, the total mass of a fuel in the reactor, in the core, is quite considerable. So it reaches, for example, in VVR, in Russian-built VVR 1000 type reactors, the mass of the fuel in the core is approximately 86 tons, and every bundle contains something like half a ton of fuel. So fuel in operation is a remarkable nuclear fuel after certain exposure to in a working reactor core is a remarkably complex material. So one of the principal feature which determines behavior of both thermomechanical behavior of the fuel and of course many chemical transformations which we will discuss today, they are governed by huge thermal gradients which prevail in the fuel pellet during the operation. So whereas in the center part of the fuel pellet, the temperature may reach more than 2000 degrees, which is close, it is still lower, but it is quite close to the temperature of melting of uranium dioxide. At the same time, at the pellet surface, the temperature should not exceed 800 degrees, and normally it is smaller. So we have huge thermal gradients, which are reaching something like 700 degrees per millimeter, which is quite a remarkable number from the materials point of view. And you can see that the structure of the fuel pellet, if we look at the structure of the fuel pellet in the beginning, we will discuss it on the next slides. It is rather homogeneous. We have uranium dioxide grains with numerous relatively numerous pores of more or less uniform size. And then when the pellet goes into the reactor, after the irradiation, after different power ramp up and ramps and cooling, the pellet cracks, forms very different internal structures, and we will discuss this in this presentation. So, fuel and operation. First of all, from let's say point of view of chemistry, there are many interesting facts. First of all, fission of uranium and of plutonium and other fissile elements produces gaseous and volatile elements. For example, like here you see a periodic table which with color-coded elements which behaves differently in the fuel. For example, green ones are volatile elements, mostly gaseous, and also elements with low temperature of evaporation. So they, of course, they migrate both to the pores and to the towards gap between the cladding and the fuel. You have during the fission process, you produce a lot of non-volatile elements, and they behave very differently depending on the particular element. They may either form isomorphous solutions, so they enter crystalline lattice of uranium dioxide. And plutonium is one of examples of element which plutonium and uranium substitute each other in the crystalline lattice of uranium dioxide. This is isomorphic solution. So some elements can make solid solution without an isomorphism. Some elements, for example, platinum group elements, they do not dissolve in the crystalline lattice of uranium dioxide, and they form precipitates which behave differently from the thermomechanical point of view. And of course, during the operation of the reactor, we have a gradual decrease of the concentration of neutron poisons. Neutron poisons are required nowadays to regulate the reactivity of the reactor core, and for such elements like gadolinium or erbium are used to moderate the reactor, to ease the control of the reactor. So in the beginning, their concentration is relatively high, and then these elements which are characterized by very high neutron cross sections, their concentration decrease. But of course, these changes in chemistry influences many other properties like thermomechanical, like thermal conductivity, electrical conductivity, and so on. Of course, we produce a lot of radiation defects, vacancies and interstitials, which partly recombine immediately after the passage of fissile fragments, but some of them, they survive. Vacancies, of course, form pores, form different clusters. Interstitials, they may also recombine or form again some more stable defects. And finally, we have a very complex and very heterogeneous thermomechanical state. And when we discuss thermomechanics and chemistry of nuclear fuel, it is important to consider porosity and grain size. So, for example, for target porosity for VVR fuel is approximately 10.5 grams per cubic centimeter with relatively small margin of acceptable margin, something like 0.1 gram per cubic centimeter. And from one point of view, we need very high density or low porosity of the fuel because it's very beneficial for thermal conductivity. You know that the thermal conductivity of uranium dioxide is quite bad, quite poor. And in the same time, when we have a low porosity, we maximize the amount of fissile material, which is, of course, good. But in the very same time, we still need some porosity because under radiation, materials swell, they increase in size, and we need some porosity to partially compensate this swelling. Also, if we have a so-called open porosity, so pores which are connected with outer space, let's say, we need open porosity because it eases some technological operations during production of ceramic fuel, for example, for removal of different binders and so on. And also open porosity helps to remove volatile fission products. And ideally, if we think from technological point of view and operational point of view, the pores should be something like 2-3 microns in size. It gives the optimum balance between swelling, mechanical strength, and so on. And also important factor, which is important for production of fuel and which is of course important for fuel in operation, is that we need relatively large grains of uranium dioxide. Because first of all, when we have large grains, we have less grain boundaries, and grain boundaries of course give some porosity, they accumulate defects and so on. And to increase the grain size, we may either adapt production process, steps of production process, such as annealing steps, atmosphere of the annealing, and so on. And we can add some additional material, some additional compounds, for example, silica or silica plus alumina or chromia or some other compounds, which are, the list is quite long. And the aim of addition of these compounds is first of all to add to crystallization, to assist crystallization of larger ceramic grains. And in addition, some of them, for example, silica and alumina, they may bound volatile elements, fission products like cesium, for example, by forming stable compounds. So there is a long list of additives to fuel which are used in Russia and in different countries. They are used in different concentrations. But the aim of these additives is, again, both influencing the crystal size of ceramics and subsequent behavior of fission products. So you can see that immediately after the production, porosity and grain size can vary dramatically. And in principle, depending on the technology, you can have a homogeneous porosity or granular porosity. So you have very small pores which are homogeneously distributed. This is a very good option. So this is basically the target option. We can have pores which are highly heterogeneously distributed. We can have pores which are unimodal, so they're characterized by small, tight size distribution. But if we deviate from the optimal procedure of fuel preparation, we can have bimodal porosity when you have smaller and larger pores. And of course, they behave differently. The same considers uranium dioxide grains. So we can have, depending on the production sequence, depending on the steps which we used, the atmospheres, the uranium oxygen ratio, and so on and so on. We can have small homogeneous grains, we can have large homogeneous grains, or grains with bimodal distribution, so have both small and large. And of course, large homogeneous grains with homogeneous porosity are optimal, and basically modern fuel is approaching this state. So, important thing when we discuss thermomechanics of fuel in operation is to consider thermal conductivity of the fuel. Recall that there is a huge gradient, thermal gradient in temperature between the central part of the fuel pellet and the periphery. And this thermal gradient is also aggravated, its influence is aggravated by very poor thermal conductivity of uranium dioxide. When you look at dependence, the compositional dependence of thermal conductivity, for example, if we take mixed oxide fuel, so it's 80% uranium and 20% of plutonium. It's a mix. It's MOX fuel. You see that depending on the exact stoichiometry, so the deviations of here, this is an ideal stoichiometry, uranium or oxygen 2, but we can have super or substoichiometric compound, which may result either from different drawbacks or caveats in the production process, or if we're not sufficiently attentive, there be some deviations from the ideal stoichiometry, we see that thermal conductivity changes dramatically. So there is an optimum, which is close to stoichiometric ratio, and then the thermal conductivity drops if we have deviations from the stoichiometric ratio. Also, if we take MOX fuel, it's real ceramics, with very high density, which is reaching 95% of theoretical maximum density. So it's close to it's basically real fuel with different oxygen to metal ratio. We see that the thermal conductivity changes considerably. So the message here is that, first of all, we have very complex behavior of thermal conductivity depending on the composition. We have a complex behavior of thermal conductivity depending on temperature. Also, since we operate in real world, this is not a fuel pellet which is floating in vacuum. The pellet interacts with surroundings. Of course, the interaction with surroundings is a function, to a large extent, is a function of mechanical properties. Obviously, when we speak about low temperatures, room temperature, or for uranium, it's up to something like 1000 degrees centigrade or a bit higher, uranium dioxide ceramics is quite brittle. And probably you recall from one of the first lectures that it is also a problem, for example, when we speak about fuel production, that ceramics is brittle. You need very high quality surface finish and so on, and it is quite difficult to achieve. When you have a mass production of brittle ceramics, it is quite difficult to avoid fragmentation, cracking, and so on and so on. And this problem is even more serious, as you know, for uranium nitride fuel. So at low temperatures, we have a brittle material, but then at high temperatures, the material becomes ductile, so it flows. And you see, again, that the temperature dependence of mechanical properties is quite complex. And this is expected for most materials, but for uranium dioxide, we have very rapid softening after certain temperature limit. So the materials start to flow. So again, when you have a large thermal gradient, in the center of the pellet, you have very high temperature. At the periphery, you have very low temperature. You have very complex behavior inside one pellet, which is less than 1 centimeter in size. You have a very complex thermomechanical state. You have a very rapidly changing thermal conductivity and thermomechanical properties. And then what's going on? So the periphery is in brittle regime or close to brittle regime. The central part is already in ductile regime. So the periphery can start cracking, and actually the fuel pellet, finally, it's of course a theoretical model, but it is quite close to the reality. Fuel pellet, after several tens of or hundreds of hours of operation, deforms from an ideal cylinder to a quite complex stuff. Neighboring fuel pellets start to interact. They start to interact with the cladding and so on and so on. And of course, appearance of all these cracks, they also influence thermal flow and so on. So fuel has a very hard fate, I would say. Also, the important thing is a creep. So how the material kind of creep is just a term, so the ability to flow to some extent. We have just radiation-induced swelling. We have a thermal creep because most materials, they start to creep at high temperatures. But we have also a radiation creep. So we have a lot of radiation defects which influence mobility or diffusivity of different species, and the material starts to creep. So it behaves very in a very complex way in physical appearance. So the pellets start to deform and very irregularly. So let's go now to more detailed understanding to what is going on in the pellet. So initial pellet is, as we know, a good fuel is characterized by homogeneous and large grains with quite small pores. Small pores means few microns in size. Very soon after going into the reactor, because we have a neutron flux, we have a flux of fission products which destroy crystalline lattice, we have very high thermal gradients and so on and so on, cracks appears. So the fuel partly behaves like a brittle material. So cracks appear at the power density of 70 watt per centimeter. At 250 watt per centimeter, fuel fragmentation starts. And at yet higher power, the fragments may start to shift and touch the cladding. So when you think about this, you have some fuel pellet in a metal tube in the cladding. And initially, there is a gap, which is gap filled with helium, for example, which separates the fuel pellet ceramics from the metal. Now you have cracked ceramic, which starts to touch, at some point, it starts to touch the cladding. So you have a strong variations in thermal flow. Sometimes at the point of the contact, you have increased thermal contact, and at the point where the gap is still open, the thermal flow is very different. After several tens of hours at full power, the pores, which form due to release of fission products, due to agglomeration of vacancies, you start to form central hole, central cavity, void. Nowadays, many fuel pellets already have this central void, central hole, which increases in size during the operation. You have very complex evolution of the shape of the grains. Due to movement of the pores start to move in the material because of evaporation and condensation. For example, you have a pore, and which is put into the strong temperature gradient, and material, the wall of the pore, which is closer, which sits at higher temperature, they start to evaporate and condense on a colder size. So the pore effectively moves. The void is moving, but movement of the pore is also combined. It leads to some recrystallization of the matrix, and you form large elongated grains. But this happens during the first hours of the operation, tens of hours of the operation. It happens mostly in the central part of the pellet, and the periphery is more or less intact. But then you may have ramps up. You can stop the reactor for some reason. You can switch it on again. So the fuels, the pellets start to crack. They behave complexly in a complex way. And at a certain point, when you have sufficient amount of volatile fission products, they start to reach fuel cladding gap, initially which was filled with helium, and this also influences temperature, the thermal conductivity. So again, you have another factor which influences operation of the reactor. Finally, after several hundreds of hours of operation, or it means that several weeks or months of the operation, the fuel cladding gap closes. And then there could be many processes. First, the cracks which are already formed in the fuel pellet, they start to become narrower, they close, because you have a mechanical interaction between the boundary, solid boundary, which is represented by cladding. So the cracks cannot open indefinitely. It may start to close. But this is, of course, a bilateral process. The cladding also experiences certain mechanical, certain ductility, and so this is indeed very difficult situation, both for the fuel and for zirconium cladding. And then you start to form inclusions of fission products, because already you have considerable number of uranium atoms which are already which underwent fission process, and then you have already sufficient number of fission products, and they start to form fission products. And of course, again, thermal conductivity decreases due to radiation defects. And what is interesting, for example, this is a part of a view, electron microscopy view of a hot particle from Chernobyl. This is basically zirconium dioxide. So this is a cladding. And here in the cladding, you see very small particles of uranium dioxide. This is scale bar is 5 microns. So they are strongly submicron. These are very small uranium dioxide particles which are inside the cladding. How did they go there? Mostly during the interaction between the fuel and the cladding during the reactor operation. So they penetrate through the different cracks and so on. So at higher burn-up degrees, we have formation of stable gas bubbles. And finally, we end up with fuel, with stable gas bubbles, with inclusions of different phases, with so-called high burn-up structure, and so on. We will discuss it. So here you see some electron microscopy images of fuel after different duration of the operation. So at minimum power, you have one structure. At high power, you have at maximum power, you have quite a different structure of the pellet. So let's look at real fuel with moderate burn-up degree. Again, this is a particle from Chernobyl. This is just a fuel which was expelled from Chernobyl reactor. This is a slice made by ion beam. So the hot particle, which consists of uranium dioxide, which was just cut by ion beam, you see numerous pores with very funny shapes. And this is quite normal because the shape of these pores, it is not just a projection of a spherical or somehow pores. They are really very rather complex in shape, and we can discuss why it is like this, but nevertheless, there is a certain direction towards the center of the fuel pellet. And what is more important, in some of these pores, you probably cannot see it very well, but believe me, if you don't see it well, you see small white dots inside some of these pores. And these white dots, I actually noticed some contamination because this is very fresh slice made in situ in electron microscope, so contamination was impossible. So these small particles are just particles of so-called 5-element phase or epsilon phase, which consist of platinum group elements plus molybdenum, technetium, and so on. We'll come to them somewhat later. So this is a real fuel which underwent operation in the reactor, but to quite a moderate degree of burn-up. Let's look at different particles from Chernobyl. Again, hot particles, which just a fuel which was expelled from the reactor. This fuel is more or less intact in the sense that you have still, you beautifully see internal structure of the pellet. You see some grains, you see some porosity, elongated pores, spherical pores, and so on. And for example, on the surface of this hot particle, you see small bubbles. It is some kind of a very heterogeneous surface, which is very typical for a fuel which underwent a certain degree of burn-up, and fission products started to accumulate at grain boundaries. So all these depressions are just places where volatile fission products were concentrated at the grain boundaries. So, but what is quite interesting that here we see not only quasi-spherical or hemispherical pores, we have also elongated pores. And these elongated pores, they form both due to thermal gradient, which prevails in operating fuel, or they may also form during thermal excursions. So when you rapidly increase the power of the reactor, so the gradient is very high. It can happen during both accidents and during some quasi-normal operations. And you may go to the situation when fission products, volatile fission products, which are close to the center of the pore, they start to try to move very rapidly from their initial location, and they form interconnected pores. This is a result of an experiment of a fuel pellet which underwent reactivity-induced accident. So the reactivity increased very rapidly. So the power supplied to the fuel increased very rapidly, and the gases start to diffuse. In the Chernobyl case, we may have also such pellets. Let's go to chemical changes. Again, sometimes people say that spent nuclear fuel is one of the most complex, chemically complex substance which human has ever made, because up to 60 elements or even more can coexist in the fuel pellet. Basically, the main fraction of the periodic table can be produced by fission, by either fission or neutron activation. So we have a very complex result of fission products, and in addition, as we remember, we have we can have a relatively complex initial composition. So uranium dioxide plus some admixtures, which are chemically quite variable, like silicon or aluminum or zirconium. So quite a large number. And behavior of these elements, of course, differs. As we already discussed, some elements, they can dissolve in the matrix, in the uranium dioxide matrix. Some elements, they tend to precipitate on the grain boundaries. Some tend to precipitate inside the ceramic grains. So you have a very, very strong heterogeneity. And this heterogeneity is also results both from granular structure of the fuel and results from thermal gradients. And what is interesting, for example, if we look at behavior of oxygen, let's consider that we have a fuel which is not, which doesn't have an optimal stoichiometry. It is either or super stoichiometric. So we have a different ratio of oxygen to metal. And this is a relative radius of the fuel pellet. So this is the center, this is periphery. We have nothing here because we have a central hole already. So you can see that the oxygen to metal ratio changes in the radial direction. These are simulations, and these simulations, they belong to relatively early stages of the reactor operation, first days, weeks, or months. Later it becomes somewhat even more complex. So, for example, oxygen diffuses forth and back depending on the initial stoichiometry of the fuel. Oxygen flow can go either to the center or to periphery, and the oxygen diffuses either by gas transport, because you always have some residual gases like carbon dioxide or carbon monoxide, which can transport oxygen and then decompose to oxygen and carbon, or you have solid state diffusion of oxygen, because actually oxygen diffuses quite rapidly in uranium dioxide. So we have evolution of your oxygen to metal ratio in the radial evolution of the oxygen to metal ratio in the pellet, and recall that this in turn influences chemistry, and the chemistry influences thermal conductivity and thermomechanical properties. Also, actinides, for example, like plutonium, they redistribute in the fuel. In the beginning of the operation, the redistribution is basically governed by different volatility of plutonium and uranium. You have a moving pore, or you have just a pore, and you have uranium matrix, uranium dioxide matrix, which has impurity of plutonium, and plutonium evaporates earlier. So you have central cavity, and the concentration of plutonium, depending on the power supply to the pellet, changes in a radial direction. And of course, this also depends on the oxygen to metal ratio, which is determined, for example, by the production process. Finally, one of the final and very remarkable chemical thing which is encountered in the field is so-called epsilon phase, which was discovered many years ago, especially on purpose. I took a photograph from the paper from 1968, when in the fuel, which experienced a relatively high degree of burnup, white inclusions were found. And these white inclusions are quite remarkable in composition. They contain platinum group elements like rhodium, palladium, and ruthenium, but they also often contain molybdenum, technetium, and many other elements actually. Not so many, but commonly these phase is called epsilon phase or 5 metal particles. But in reality, the composition may be more complex. And actually there is a huge, no, relatively large variations in the exact compositions. And if we look with transmission electron microscopy, we come to the conclusion that most of these particles, they combine both small crystallites, small, it means several nanometers or tens of nanometers, which are embedded in the amorphous matrix of this metal. And this epsilon phase is actually not just, it can be quite resistant in different environments. For example, here you see an example of a quite an interesting object from Chernobyl, which was collected 5 years after the accident in so-called under-reactor room, which was directly after below the reactor core. And when the reactor was destroying, in the process of destruction, some material from the reactor, namely the so-called corium, so the product of interaction of uranium dioxide fuel with cladding, was expelled into this under reactor room. And actually this is just a piece of steel, metal tube, iron tube, which was used to supply water to the reactor. And we look at this metal tube, you have some slug-like material is attached to this. So it just flew from the destroyed reactor core and flew for 10 meters and went to the tube. And inside this slag, which basically consists of iron oxides, we can find tiny particles. Tiny, it means here they are something like 200 nanometers. They're submicron particles, but actually these submicron particles are exactly epsilon phase. So these epsilon phase particles, they're relatively resistant to the environment. And actually, if you recall that many of them contain platinum group elements, for example, these epsilon particles, they survive dissolution of the fuel in nitric acid. And what is even possibly more remarkable is that kind of an epsilon phase particles, they can be found even in irradiated graphite, but this is a very peculiar type of irradiated graphite from one of the Russian reactors, which was operating for 50 years, and it underwent certain accidents when the whole core, first of all, the fuel cladding was destroyed, so there was an accident, fuel went into the graphite, then it was, the reactor core was filled with water. Very distantly, it's similar to what is going on in Fukushima, but very distantly. And then this reactor continued operation for several tens of years, and you have very remarkable precipitates, which are very tiny. They are something like 1 micron in size. These are precipitates of fission products, which are resistant to leaching and resistant to different acidic treatment. So again, these are 5 metal particles, but if you look at their composition, it is very difficult to make to measure their composition exactly because they're very small. Again, I recall that they're something like less than 1 micron in size. But nevertheless, you see very large variations in chemical composition. We have variations in molybdenum, for example, concentration, molybdenum-ruthenium ratio, which implies that these particles came from fuel, which was pieces of fuel which were at different directions from the fuel, from the center of the fuel rod. One of the most remarkable and still poorly understood feature of oxide fuel which underwent very high burn-up degree is formation of so-called high burn-up structure. Again, this high burn-up structure was found many years ago, and that's more than 50 years ago. It's still not completely understood how does it forms. It forms at very high burn-up degrees. We saw already that concentration of the fraction of plutonium which changes in radial direction, and plutonium initially concentrate mostly on in the central part of the fuel pellet, then it goes down its concentration and then goes up, but at very high degrees of burn up due to so-called resonance nature of neutron capture by uranium-238 oxide isotope, we have a very high concentration. Finally, we produce more plutonium at the very edge, at the periphery of the fuel pellet. And this leads to very high temperature release, thermal power release at the external part of the fuel pellet. This structure starts to be visible at very high burn-ups, exceeding something like 60 megawatts per day per kilogram of uranium. And this phase is characterized by very, very small grains with very high porosity, and these grains are just several tens or 100 nanometers in size. In scanning electron microscopy, you see the variations in the pore size and in structure of the material. This is the center of the pellet, this is the periphery, and you see some kind of a highly granular material. If you look at transmission electron microscope, you see very, very small grains of uranium dioxide with a lot of newly formed grain boundaries. And there are still discussions about how these high burn-up structure forms. Most likely, this is a solid-state physics process, so it is related to dislocations, which in turn appear due to excessive concentration of radiation defects. But nevertheless, this is a very interesting structure. And this structure is becoming more and more important because nuclear energetic is going to very high burn-ups. So these, the thickness of this high burn-up structure layer will increases with time. So, and now I will speak a little bit about the behavior of materials during nuclear accidents. Okay, you know these, you likely know these images from Chernobyl accident. So the reactor core is completely destroyed. And if you look at the cross-section of the reactor, so this is called so-called shelter. The reactor itself was here. Here in the red, you see the Chernobyl lava. We will speak about them. And just to understand the scale, this is so-called biological shield, upper biological shield, and this is human for the size. This is not from Chernobyl, but it is from identical reactor in Ignalina nuclear power station, which is now in Litva, which is now closed due to political reasons. Nevertheless, you see that these detail is fairly large, and this detail, and which is connected to the bottom, there are two identical details. The size, this is a human, and it weighs several thousand tons. And you can see that during the Chernobyl explosion, the upper lid was thrown up and fell down. So the power of the explosion was enormous. To destroy all these tubes and to throw up such a heavy thing, you need quite a considerable power. And actually, unfortunately, there are many, many nuclear accidents of different severity. So very much not exclusive list of the reactor accidents which has happened starting from 1952 is given here, but actually this list is quite extensive. Only main accidents are listed here. So there are two main types of nuclear accidents, which of course has different influence on the reactor fuel. You can have so-called LOCA, loss of coolant accidents, which proceeds on a time scale of minutes or tens of minutes. And you see here the optical photograph of an experimental core which was destroyed in a loco-type accident, and you can have reactivity-induced accident. Reactivity-induced accidents were quite common in the beginning of nuclear era. They are not so common now, but for example, Chernobyl accident was clearly a reactivity-induced one. So it proceeds very rapidly. So for some reason, there are many different possibilities. You supply a lot of energy. You can have a new, for example, neutron pulse, which dramatically increases neutron power on a very short time scale. And again, there is a very big difference in time scales of these types of accident. So what's going on with fuel? When we have a small thermal surge or power surge, the fuel is more or less intact. It might fuel pellet might have touched the cladding, but for a very short time without very strong consequences. If you have larger energy release, fuel cracks, and finally fuel may fragments completely. And of course, it turns out it blows out the cladding. And then imagine that you have a fuel pellet, fuel bundle, which is in some thermal carrier, for example, in overheated supercritical water. And then suddenly you have a lot of small, very hot particles which goes into water. You have a vapor explosion. So this is quite typical, is typical representation taken from, of course, from an experiment, but such accidents, they lead to very strong and very rapid power release and may lead to vapor explosion. But as we already said, that reactivity-induced type accidents are quite rare now for a number of reasons. Operators of reactors are more skillful now than they were 30, 40 years ago. They understand how a reactor behaves in different regimes, so reactivity-induced accidents are not very common now. But loss of coolant accidents may happen, and they had unfortunately happened quite a number of times in different countries. Basically, in all countries operating nuclear reactors, small or large-scale type of local type accidents has occurred. What's going on when we lose the coolant? So the temperature first starts to increase. The reactor core is drying up because the fuel releases heat. There is no sink of this heat, and of course, fluid starts to evaporate. There could be some steam generation. And the fuel rods start to heat, initially relatively slowly. But of course, it is always debatable what is slow or fast, but it's approximately 1 degree per second. What is important that at 830 degrees zircaloy, of course, the exact temperature depends on the exact zircaloy composition. Zircaloy starts to swell. And of course, fuel starts to interact with zircaloy, so we have a very, again, complex thermomechanical interaction. And hydrogen starts to be generated. And at 1230 degrees, zircaloy starts to oxidate very rapidly by steam. A very important steam generation reaction, which produces a lot of hydrogen and a lot of heat. And of course, hydrogen in air forms an explosive mixture, of course, in quite actually broad range of composition of ratios of oxygen to hydrogen. It's still explosive. And this reaction is exothermic and it is self-sustained. So it goes up and heats more rapidly. But actually, when people say that this reaction is immediate, it's kind of an exaggeration because, for example, the temperature rise, the temperature ramp is something like 5 to 10 degrees per second. And so to reach very bad consequences, you have still several hundreds of seconds. But several hundred seconds, is it a lot or it is not much? It, of course, depends on your situation. If you are an operator of a reactor which is in trouble, you have less than 2 minutes to think what's going on and to make some countermeasures. It's not much. But from the point of view of experimental physics, for example, this heating rate is not a lot. So when people say that this reaction is immediate, it is quite an exaggeration. But then a zircaloy starts to react. First, we generate heat, we generate hydrogen, which may explode. And finally, zircaloy starts to react with steel from spacers. And at yet higher temperatures, the melt, which has formed during the interaction of zirconium, zircaloy with steel, starts to move and so on. And yet higher temperatures, which may, and they have reached, for example, at 3 Mile Island accident, the maximum temperature certainly exceeded 2,500 degrees. You melt uranium dioxide fuel, which forms so-called corium, so a mixture of uranium dioxide and zirconium dioxide. And again, people has made a lot of experiments to understand how this how fuel behaves in different conditions. But the majority of these experiments are, of course, performed with non-irradiated fuel, because spent fuel or irradiated fuel is extremely radioactive, and you have to be very careful when working with it. You can work with it only in dedicated facilities. You are limited in number of analytical techniques and so on and so on. And so the majority of experiments are performed on non-irradiated fuel. But nevertheless, there were some experiments which, when people compared behavior of uranium dioxide, which is embedded into zirconium dioxide, into the clay, into cladding, and people compared unirradiated and irradiated uranium dioxide fuel. And you see that the difference is quite dramatical, both for MOX fuel and for pure uranium dioxide fuel. So non-irradiated fuel behaves in a more predictable way than irradiated one. And so in actual experiments, we unfortunately have to deal with irradiated fuel, and therefore the experiments which model on a small scale, on a laboratory scale, which model fuel zircaloy reactions are not always very reliable, I would say. Let's go now to large-scale accidents, not to experiments, but to large-scale accidents. For example, in case of Chernobyl again, you have a destroyed reactor core. You have numerous fuel bundles which are just scattered around. There is no cooling. And of course, there is a lot of construction materials which just fell over these destroyed fuel bundles. And if you make a very simple thermomechanical modeling, if you have, for example, 16 bundles soon, immediately after the interruption of the reactor operation, you cover them with thermal insulation and the temperature rises very rapidly. Why is this? Is that because immediately after the stop scram or immediate stop of the reactor operation, the residual heat release is approximately 6% of the operational power. So you probably know this, but this is one of the reasons when people often from general public often ask, why cannot we just switch off the reactor? Why should we cool it? Because the residual heat generation is very considerable. Of course, the amount of this heat decreases with time relatively rapidly, but immediately after the scram, or emergency arrest of the reactor, it is quite considerable. So if you have 16 bundles, the temperature goes to, of course, these are just the numbers, but nevertheless, they're quite considerable. So it's approximately 2000 degrees. If you have a larger selection of bundles, you can have temperatures basically anything you want. Of course, there are many limits to these calculations, but nevertheless, the general sequence is quite clear. So what's going on when uranium dioxide fuel has reacted with zircaloy? Of course, zircaloy starts to be oxidized, so it is uranium O2, zirconium O2 mixture, which is called corium, starts to interact with concrete or sand, the material of the reactor building. These are small-scale experiments. You see some kind of a glassy material, glassy ceramics is formed. These are images of a large-scale experiments volcano, which was performed in France by Commissariat de l'Énergie Atomique. So more than 100 of corium was molten in induction oven and then immediately poured into the concrete. You see some nice thermal images. These corium melt distributes very rapidly. It has very high flow ability. It flows rapidly. It interacts with concrete. It destroys it, and you can have a very complex interaction between concrete and this corium. And well, let's consider all these some possible processes on case of Chernobyl accident. First of all, what's going on during reactor instabilities prior to the explosion? We probably form some precursors to some hot particles which were later expelled from the reactors. And we also recall that we have found epsilon type particles which are inherited from a fuel in a material which has interacted with surroundings for very little time. When the reactor is actually destroyed during the explosion, we mostly produce hot particles. But in subsequent events, when the fuel which still rests in the reactor building starts to interact with construction materials, we see formation of so-called lava-like fuel-containing materials, which are sometimes called Chernobyl lava, and this lava starts to interact with concrete. And now Chernobyl lavas, they generate aerosols, which are distributed more or less now inside the shelter, but in principle they can go outside. Here are the actual photographs of Chernobyl lavas. You see different types of these ceramics, which are different in the chemical composition, but basically all of them are just silicate glass with quite high concentration of uranium, zirconium, and so on. And I don't know if it will work. Probably it will work. It is this is real X-ray tomography of Chernobyl lava piece. You see many inclusions. It's one piece, it's the second piece, optical photograph. You see very considerable number of different inclusions in them. What are these inclusions? So first we have, of course, fuel. Basically uranium dioxide fuel, which always contains some pieces of zirconium. So this is kind of a spent nuclear fuel which has interacted with cladding. But nevertheless, it has all features of initial uranium dioxide fuel, but with some admixtures of zirconium, sometimes with iron and some other elements. We have oxides. Basically zirconium dioxide, very often, in most cases, with admixture of uranium. So of course, this is a product of oxidation of the cladding. We have some steel droplets and uranium-rich zircon or zirconium silicate. Zirconium silicate is actually forming at quite late stages, several days after the accident. But what is quite interesting, just to give you some understanding of the scale of the processes, here you see a steel droplet. Droplet, as we all understand, the matrix is glass. Droplet, as we understand, means that the material was molten. Melting temperature of the steel is approximately 1500 C. So for several days, at least for 1 week, the temperature of the lava generating volume exceeded 1500 C. So for example, in 3 Mile Island accident in the United States in 1978, the temperature definitely exceeded 2000 degrees. So uranium-based grains, uranium dioxide-based grains, you have very nice precipitates. Again, just a fuel, kind of a fuel, spent nuclear fuel. Here we don't see, for example, epsilon-type particles because most likely they have dissolved in the glass. We don't know why, but simply, most likely, we don't find them because their absolute number is quite small. And actually, the amount of the lava is many hundreds of tons, 1,000 tons, and it is quite difficult to find very small particles which are randomly distributed. We have very interesting conclusions of oxidized cladding. Oxidized cladding is, of course, zirconium dioxide with a mixture of uranium. But what is important is zirconium dioxide, which is known as badilliite. Badilliite is quite common mineral, zirconium-bearing mineral, but when you make zirconium dioxide at high temperatures, it goes to whereas badilliite, or so-called monoclinic zirconium dioxide, is a low-temperature modification. At high temperatures, zirconium dioxide adopts tetragonal or even cubic phase, which can be stabilized by some impurities when you cool down. But what is important is that inclusions of this zirconium dioxide, they start to crack. And actually, this cracking of the glass matrix results from interaction of zirconium dioxide, for example, with moisture. So in principle, you have relatively stable glass with some inclusions, and some of these inclusions, they may underwent phase transformations due to interaction with atmospheric moisture. And this interaction may lead to cracking of the lava. And some hot particles gives us kind of a representation of what was going on during the early stages of the experiment. So this is one hot particle. The size you see something like 300 microns, so 0.3 millimeters. And when you look at high magnification with electron microscope, you see that the matrix is extremely slow. Gray one is zirconium dioxide. White drops, white points is precipitates of uranium dioxide. And here, certainly, you have some traces of thermoplastic flow. So uranium dioxide was interacting with cladding, and the cladding was ductile, so it was flowing. And when it was cooling down rapidly, when the particle was expelled, there was a very interesting, from crystallographic point of view, precipitation of crystallographically ordered phase. And by investigation of these materials which result from the accident, we can make some conclusions about how the Chernobyl accident actually progressed. Because by investigation of hot particles of this corium material of lava, we can understand at which moments of the accident progression they were formed, and make some conclusions about how this was developing. Well, I think that probably this can be a finish of this, the end of this small introductory lecture. Of course, spent nuclear fuel is a remarkably complex thing, which can be investigated from very different points of view, from physics, chemistry, material science, and so on. And it's quite obvious that, like many other subjects which were discussed during the school, 1 hour is insufficient to discuss it in any details, and this was just a very brief introduction, maybe. Thank you for your attention. Okay.
So, any questions?
Thank you very much for the interesting presentation. So my question is about the spent nuclear fuel. You know, after usage, it's still very hot, about 2000 Fahrenheit. That's about 1000 something degrees. Is there any innovative use of this heat instead of just letting it go to, let me say, quote unquote, waste, like the residual heat from the spent nuclear fuel? Any innovative use, what we can use it for?
Residual heat?
Yes, the heat, for something beneficial.
Frankly speaking, I don't know, because usually residual heat is an obstacle, because you stop down the reactor for regular maintenance and so on, and this heat is released. Normally, this heat is still, if it is 6% of the reactor power, it is basically insufficient to make vapor, for example, to make steam. So it is very difficult probably to make steam from in this situation. So I think that it is very difficult to make something innovative in this sense, because this heat is just released. It's kind of an exhaust. I doubt, actually. Actually, to some extent, Chernobyl accident it is again very large oversimplification, but the reason of Chernobyl accident is partly an attempt to kind of use something like this. This was unplanned experiment. It was quite different. If we go to details, details are different. But you may say that it is kind of similar to an attempt to use the residual heat generation.
Okay, thank you.
Actually, it decreases quite rapidly. So in several days or weeks. Heat of spent nuclear fuel, as you know. Well, first of all, spent nuclear fuel is extremely radioactive. So anyway, you have to cool it down. And cooling down, it means both decrease of thermal heat and decrease of radiation load. Radiation load from spent nuclear fuel is very high. If you take fresh nuclear fuel, you can hold it in your hands. If you go to spent nuclear fuel, basically you die within several minutes. So it is quite difficult to use it in a constructive way.
Okay. I have one small question about this corium experiments in France. Did they use just uranium dioxide, or it was the full mixture of the elements, like 50 or 60 elements?
No. This was basically uranium dioxide with some iron with zirconium. If you think about this, it is quite difficult to heat simultaneously something like 200 kilograms in a special oven from which you can pour it out. And this was done in an inductive oven. But the principal oversimplification of this event is that you have 100 kilograms, yes, or 200 kilograms. That's a lot, but if you think about the normal reactor, it's several tens of tons. Mm-hmm. So the kinetics of cooling down is dramatically different. So in France, everything was cooled down in few tens of minutes. In Fukushima or Chernobyl, it takes days.
Okay. Yep.
Thank you for the very interesting presentation. My question is that it seems like there is a lot of useful data that can be gathered from research like this. Is this used as an investigation to figure out what caused the accident exactly, how it could be prevented? Or is it also used perhaps to develop better techniques to make the fuel, to make the cladding? Of course, we don't really want accidents to happen, but if they happen somehow that the outcome is better or more manageable or something like that?
Actually, if we speak about large-scale accidents like 3 Mile Island or Chernobyl, from the point of view of reactor physics, the reasons of the accident were quite clear quite rapidly. So after the initial assessment, during several months, for example, or even weeks, it was more or less clear what exactly has caused the accident. It is not a big problem from the reactor point of view, reactor physics point of view. Reactor physics is relatively well understood, I would say. From the point of materials interaction, of course, 3 Mile Island and to a smaller extent Chernobyl accident, they initiated formation, for example, of accident-tolerant fuel. The fuel which is less prone to loco-type experiments, so it doesn't destroy that rapidly. You can try to increase thermal conductivity. You can try to reduce chemical aggressivity of these melts. also in modern type reactors, for example, Russian built reactors like VVR, which is now made in India and in China, they have a trap for corium. So even if the accident has happened, of course, the reactor physicist has worked a lot to reduce this probability, but okay, it has happened. Then you can make a special compartment in the reactor building which traps the corium and cools it very rapidly. And the main efforts in for making in this corium trap was to create special types of so-called sacrificial materials. The materials, the concrete, for example, types of concrete which interacts with molten corium and cool it down very rapidly.
Any more questions? Yeah.
My question is, what is the actual purpose of central hole in fuel pellet?
Of central hole,
Yes.
it's of central hole is mostly to it affects again thermomechanical properties, because as you remember, it affects both distribution of volatile elements and thermomechanical behavior. Because if you have a pellet which is, let's say, solid, when it starts to deform mechanically, it starts to interact with neighboring pellets. And then when you have two pellets which are very in solid contact, they start to expand in radial direction, and they start to interact with cladding, and they can blow up the cladding. So, and second, it is kind of more or less you have a prescribed place for volatile elements. Of course, this central void will form anyway, but you can have some kind of a preferential site for volatiles. So both thermomechanics and let's say chemistry.
Thank you. One more maybe small question about the equipment for such analytical studies of the irradiated fuel. Do people use just a conventional, I don't know, scanning electron microscopes, or it is some specific equipment special designed?
No, of course, spent nuclear fuel, due to regulations, you cannot study them in a normal laboratory. That limits actually the analytical possibilities, because in principle, you can use all normal analytical methods to investigate spent fuel, like electron microscopy, different thermal electrical conductivity measurements. But most of them has to be performed in hot cells. And this limits a lot the availability of different analytical techniques. Nowadays, it is kind of being circumvented by placing by so-called nuclearization of different analytical equipment. For example, making Raman spectrometers which operate in hot cells or scanning electron microscopes. With transmission electron microscopy, it's relatively easy because the sample is very small. But for most other techniques, people are severely limited by radioactivity, unfortunately.
Okay, thank you. Any more questions? If no, then let's thank the speaker again.
Thank you. Thank you for your attention.
Thank you very much. So now we have a break before the next lecture.
Андрей Александрович, здравствуйте. Слышите меня?
Да, добрый день. Слышно
Да,
меня?
здравствуйте. Так, мы вас тоже слышим. Прекрасно.
Отлично.
Пока только черный экран.
Так, сейчас, секунду.
Попробуйте включить демонстрацию, да.
Сейчас вот.
Вас видим.
Так, я пока камеру отключу, чтобы у меня интернет не тратился. И демонстрацию экрана настрою. Так, организатор отключил демонстрацию для участников. Наверное, с вашей стороны надо разрешить.
Попробуйте еще раз.
Так, сейчас. Так, что-то не получается. Сейчас еще раз пробую. Так.
Отлично.
Видно?
Да, все прекрасно видно, да. Спасибо. Все, тогда через 5 минуточек начинаем.
Хорошо, спасибо.
Hey, dear colleagues, please take your seats. So here we have our second today's lecture with Andrei Bundin from Ghost Corporation Netherlands. Andrei, can you hear me?
Yeah. Good
Yes.
afternoon, dear colleagues.
Good afternoon. Okay, please.
Okay, my name is Andrei Bundin. I'm the research executive in Neolan Group of companies. We'll start with saying 2 words about our company. Our company is a private software and engineering company. We have more than 20 years experience in developing digital products for different industries, including atomic industry, nuclear industry, and as well as different nuclear facility life stages. Mostly, we are concentrated on decommissioning stages. And today, I will present you the technologies that we use for this topic for decommissioning of radiochemical facilities. As you may know, there are several huge radiochemical facilities in Russia. There is some industrial ones and some laboratories. Among the biggest, it's three radiochemical plants, one in Ozersk, one in Zheleznogorsk, and one in Seversk. So all of these plants, they have a very long story. And the most oldest one in Ozersk, it was found in 1949. And all these objects, they have a lot of legacy facilities which is now are shut down and are under decommissioning procedures. One of the biggest one is in Seversk. It's quite old, and it's the largest of all radiochemical plants in Russia. The whole site contains more than 20 buildings, and almost half of them are legacy facilities. To do decommissioning, we face a lot of challenges. First of all, it is the radiochemical sites. They are quite huge. They have a huge amount of systems, different structures, components, elements, and so forth. And all they have very complex engineering configuration of the main buildings, main system, secondary system. As far as these facilities are old, they have a lack of initial design and engineering documentation. Some of the documentation were lost during all these years. Some of them is just inaccurate. So that's also a huge problem. And another kind of problem is that a lot of facilities, they have a very strong radiation contamination that contains the uranium, plutonium group, actinides, and some of the equipment has a very, very high level radioactivity. So that puts a lot of limits to their personnel interactions in these areas. These are the main decommissioning activities that we have. It first starts with planning, then we do physical and radiation characterization of the facility. We plan the decontamination, dismantling, and of course, we put a lot of attention to the raw management, radioactive waste management, because during these dismantle procedures, there is a huge amount of different levels of radioactive waste generated. But today we will put our focus on the second stage, which is physical and radiological characterization. That is a very, very important stage for all the decommissioning process, because this stage allows us to collect all the engineering data that we need to proceed the decommissioning planning, design, and all the subsequent procedures. So during this phase, we obtain different data to understand the facility's engineering configuration of its systems, structures, components. We do materials inventory. We need to collect the radiation data to understand the radiation situation, and also to estimate the amounts and categories of radioactive waste before we start the dismantle procedures. As far as these tasks needs a huge amount of data. We can't handle all this data with traditional workflow, paper workflow, or just traditional instruments. We use a set of digital tools. Here you can see the typical stack of applied digital technologies that we use. First of all, it's building informational modeling. We develop a 3D BIM model of all the facility and put all the engineering and operation data inside the model. So this model serves as a single source of true and actual information. We use reality capture tools. That means we use laser scanning and spherical photopanoramas to capture the actual information of the facilities, because most of them are old and don't have a appropriate design documentation. Then we proceed characterization. That means we provide physical and radiological survey of all the buildings, all the systems, and all the site around the facilities. Then we use radiation calculation tools to simulate and to calculate the levels of radiation, the radiation dose rate fields, and estimate the amount of radioactive waste that we will generate. And we have a set of tools for analytics, for reports generation. So typically, BIM model starts from making a 3D representation of all the facility systems, structures, and components. Here you can see an example of a BIM model of one of the nuclear facilities. The model is strongly connected with engineering data management system. So every element of the model has its attributive information that contains data about its physical characteristics, spatial characteristics, size, weight, materials, the position inside the building, the part of each system it is. It's also connected with this design documentation. We can easily switch between the different elements, between the attributic data, between the drawings, draftings, and then we can also move from the single equipment to the whole system and also see its integrated attributes of all the system and of each element of the system. We could switch to the drawings. We have, if the drawings are old, we just do this scanning and put the electronic copy of these drawings inside our database, which is also connected to the BIM model. Then we can have a 3D representation of all the systems. Let's say we need different like pumps, vessels, tubes. We can generate different reports that contains all the information about the systems. So we also download the results of laser scanning and spherical photopanoramas, and these photopanoramas can be synchronized with 3D model, and it will provide the actual information for the engineers that provide nuclear decommissioning and planning. Having all the engineering data is not enough for proper decommissioning. We used here in our technologies, we use the next layer of data. It's radiological data. This kind of data needs to estimate the radioactive waste that we will have during decommissioning, and to estimate the radiation situation, as well as provide some more simulations of radiation situation change as long as we do dismantling procedures. Here I will tell you something about how we do this radiation model and integrate it inside our BIM model. First, we start with some preparation and initial analysis. Here is just an example like of a compartment that contains different equipment. Before starting our procedures, we usually invite the specialist from the facility that points which of the equipment could be radioactively contaminated or contain some radiation sources, and which are relatively cleaned. So we divide all the equipment inside the area as radiation sources and as barriers. Then we do some modeling and applying mathematical algorithm. And to simplify the procedure, we use so-called phantoms. Phantoms is the simple representation of equipment usually with simple geometrical objects like cubes, cylinders, spheres, or the group of objects. That's what we do in the first step. Then the radiation survey specialists, they know which of the equipment could be a radiation source and which one could be a barrier. Then they set a points of measurements. The points are set directly inside the beam model, so the number of points should be enough for subsequent modeling. So, and every point is linked to the equipment or just a inner coordinate system inside the model. After the measurement points are set, we provide the characterization task planning. Usually, task planning means we develop a procedures, step-by-step algorithm, what we should measure, what tools we should use, and what information we should obtain with all these measurements. When specialists goes just on site, they use mobile devices like these industrial tablets with preload beam model of a facility, or which is more typically the certain area, rooms, compartments. In these tablets, they can see the task they have. They see what points they should be what points they should go in, and what kind of measurements they should do, whether it's dose rate measurements or alpha beta counting or swipe sampling. All the information obtained from measurements is inputted in these tablets and after goes directly to the beam model for subsequent collection and procedure. After all the information is collected, we obtain a huge amount of the radiological information connected to the beam model and connected to the geometry of the facility. After that, we can automatically generate different kind of radiological survey reports. But the collected data, the measured data is usually not enough for our task. We use the measured data to provide some calculation and estimation. We typically solve so-called inverse and direct task. Inverse task is finding the specific activities of phantoms and as well as beam model elements with using of these phantom characteristics like geometry, its material, and obtained dose rate measurements results. So we applied a specific mathematical algorithms which contains systems of equations and numerical methods for calculation. And in the result, we obtain the specific activity of each element, of each beam element here, that was previously defined as a radiation source. We use this information to calculate the radioactive waste. So we know the specific activity of equipment as well as we know its physical characteristics like weight, material, its dimensions and so forth. And we understand how we would dismantle it. So we can estimate the amount of radioactive waste of each categories that would help us in future for proper decommissioning, dismantling planning. Let's say here is just some screenshots of how we apply the systems. You can see some tables, some calculation about some calculation of radioactive waste generated, and it's automatically separation along its categories. And also we can provide some automatically report generation for this. Then we solve the direct task. The direct task is finding the dose rate volumes distribution with using of specific activity of elements that we calculated previously, and its configuration inside the beam model. The results are typically used for radiation safety assessment and radiation simulation as far as we provide dismantling process. Usually we do verification of our results. So we obtain the three-dimensional field of dose rates, and then we compare the meaning of the dose rates in a certain point with the meaning of the measured dose rates. And if it's matched, so that's how we understand that our model is quite true for this situation. So here we can switch between the 3D views, or we can obtain the dose distribution at any point, at any cross section of the given area. And then we use this for making simulation in dismantling operation. Here you can see the 3D model with this dose rate field distribution. We have some equipment, radioactive equipment, which is as a source. And then we, one by one, we just delete these elements and see how our dose rate field will change. Changing this sequence of dismantling, we can understand which is the most appropriate way, especially taking into account that we need to provide the most safety environment for personnel that will do these dismantling works according to this ALARA principle. After that, of course, we use analytical tools to provide specific reports about the result of measurement, about the radiation situation on site. So that was a little bit theory. Now I will provide you with some of the recent case studies. Here is the radiochemical plant in Seversk. It has a lot of challenges that we faced. First of all, it has only 60% of initial design documentation that were available for any planning purposes. And only 30% of these 60% were containing actual as-is sites and facilities configuration. Around 10 years ago, another organization provided radiological and physical characterization of the site. And they relied only on initial design documentation. That made a huge risk. If nowadays we use these results, we could make a huge mistake in decommissioning planning and subsequent estimations. So to make the proper radiological and physical survey, we used our beam modeling and reality capture tools. First of all, we developed a beam model that were based only on the initial design documentation. Here you can see just some screenshots of these documentations. Most of it's quite old. It's just more than 50, 60 years old. And altogether, we find and scanned more than 12,000 documentations that contains more than 40,000 pages, lists, drawings, and so forth. And we draw out more than 200,000 attributes, which is physical engineering characteristics of the equipment. That was the first step. The second step, we did laser scanning. We provide laser scanning of all the facilities, compartments, areas, and added this information after point cloud recognition inside the beam model. So we corrected our beam model to reflect the actual engineering configuration of the facility. Also, we did spherical photopanoramas just to give an impression of the actual state of the facilities and its inside compartments. Overall, we made more than 2,000 positions points for laser scanning and more than 3,000 spherical photopanoramas. including inside and outside areas. So we obtained a comprehensive beam model of all the facility. We can move from the site model, which is you can see in the left top part, to the buildings levels, and from building to the compartments levels, and from the compartments to the certain equipment levels. We can obtain the characteristics of any of these assets, and we can provide some search and 3D navigation inside the beam model. So the final model of the site contains more than 400,000 elements and more than 10 million attributes. That was one of the most biggest beam model of the nuclear facility we ever made. Here is just an example. In the left, you can see the 3D model of the compartment that was built only by initial design documentation. And in the center, it's the model that were made with also using a laser scanning. And on the right, it's just a photography of the area. So you can see the difference could be really huge, and that affects on all the subsequent procedures of decommissioning planning. Here is another example of the same situation. Yeah, you can see in the left up, it's just what was made from the initial design documentation. Then we did laser scanning, and in the right, we obtained the real engineering configuration situation. And again, the future is quite different. So we used all these models for three main procedure. For further planning, we automatically obtained equipment specifications. It's a list of huge number of equipment that is inside with its characteristics. Then we did radioactive waste estimation and categorization. It's another part of the planning documentation. And we reconstruct the design documentation. So now, after applying these beam instruments, we obtain the full set of design documentation. That was a great advantage, because the initial design documentation were old and not actual in most of the cases. So after that, we provide a lot of different analytics. We can upload the compartment characteristics, general 3D views, plans, physical and radiation data. We can provide these estimations, generate the corresponding reports. We can make a task generation for dismantling and provide estimation of the resources we need, like money, humans, like special tools, techniques, and so on. We can also estimate the personnel dose exposures for the certain rooms, areas, and works. And we can generate the list of dismantle tools and personal protective equipment that we'll need to use during these dismantle procedures. Okay, that's what we have. And now that is not only technologies that will help us to do the proper decommissioning. Of course, we are working on the next level of technologies. And now I'll tell you something about our future research and development. So if we have an areas of a nuclear facility that is quite unavailable for humans to proceed this radiological and physical survey, we can use robotic systems and drone system. Here is an example of using the small drone system equipped with different sensors for capturing physical characteristics as well as radiation characteristics. We developed the technologies that use this hive of drones, the group of drones that are equipped with these sensors and controlled through the flight missions with special indoor navigation systems. The drones flies around the area and provides laser scanning and collects all the data, all the point cloud data inside the software, which is afterwards proceed and we obtain the 3D model of the area, as well as its characteristics, both physical characteristics and radiological characteristics. And the final model contains all this information, so we can easily switch between different elements and see its attributive data. Another research we made with using not drones but smart robotics, like robotic dog systems. Almost this year in summer, we did some experimental radiological and physical survey for one of the nuclear facilities. We used the robotic dog from Deep Robotics Systems and equipped this robotic dog with sensors, with laser scanning, with photopanoramic camera, and with dose rate measurements equipment. And we did some survey of an area. In the left, you can see the result of the laser scanning. As far as it was experimental part, you even can see some personnel on the picture. And on the right side, we have the statical photopanoramas of the same area. Here is the result of our beam model development. So we transform this point cloud into the 3D representations and download there the physical attributes, radiological measured attributes, and now we can see we can have the 3D model synchronized with photopanoramic. And example you can see on these pictures. We can navigate inside the model to have the visual representation of the facility and its compartments inside. We can also obtain the characterization attributes, like we can choose the elements and see in the right area all the attributes that is needed for subsequent decommissioning. The beam model is quite accurate, so it's even possible to see the wires and cables up to several centimeters in diameter, so it has a very high level of detail. And then we provide the radiological calculations. As I've told before, we calculated the specific activities of the element, and then by solving the direct task, we could simulate the radiation situation. So here is just the result of these simulations. Okay, and making a conclusion, once again, I'll just repeat the main advantages of this set of technologies that we applied. First of all, beam model serves as a single source of information for the facility. Also, it contains the actual data sets for both for physical and for radiological data. It serves also like a collaboration environment. So using the web technologies, several teams can work in the same digital environment. Each one can proceed its own task, like engineering, survey things, design procedures, planning, calculation, and so forth. It gives us the very, very efficient tool for high accuracy of radioactive waste estimation and categorization. And also it has tools for data management, for decommissioning planning, and data management for future project works, which is like project management tool. So that was like the brief introduction and case study of our technologies. Now I am ready to answer all your questions if you have. Thank you for attention.
Andre, thank you so much. Colleagues, any questions? No questions. Okay, may I ask one?
Yes.
Do you really need these old documents and pictures instead of these BIM photo images? I mean,
the design documentation usually used for also used for planning, because we have some regulations and rules that make us to produce a paper documentation, and this paper documentation should contain all these drawings, drafts, and all these connected data. It always depends on the regulations. Unfortunately, we can't work only in this 3D environment. We can do this technically, but officially, we also need to duplicate the work in the traditional paper work.
Yeah, I see things. Yeah, questions.
Thank you for the very nice presentation. My question is, if it comes to the decommissioning and the actual deconstruction of the building and taking away the material, the personnel who works there, do they have to be in a position where they wear the dose meters and considered workers with radioactivity, or is it manageable enough that this can be avoided?
Okay, thank you for the question. Yes, every personnel should have these dose rate dosimeters and equipment because it's obligatory by the rules, radiation safety rules. But we had this simulation, and before we have a plan for dismantle procedures for deconstruction, we see what actions can we do to minimize the risk of radiation contamination and radiation exposure to the personnel. But despite of this, anyways, the personnel always has its own personal dosimeters when they work.
No question?
Thank you for the interesting presentation. So, in the presentation, you mentioned the plant in the radiochemical facility in Siversk. Yeah, so I know of Sibirsky Chemichesky Combinat. I don't know if that is the plant you're talking about, and then it's been in operation since I think 1948. And do you have a lifespan for these radiochemical facilities, and then how long does it take to decommission them?
Yes, thank you for the question. This facility is in Seversk. Yeah, it's part of Siberian chemical plant. The plant was founded in the late 1930s, but this radiochemical plant was built a little bit later, like 20 years later. And now most of this, I would say like 70% is the legacy facilities. And they are under decommissioning, or they will be under decommissioning in the next like 10 years. There is, as far as I know, there is no plan to make a new radiochemical processing in this site especially. So as far as I expect, during like the next 15 years, I think 100% of all these facilities will be decommissioned, under decommissioning.
Okay, thank you so much. Colleagues, any more questions? Okay, let's thanks to our lecturer one more time. Andrei, thank you.
Thank you, colleagues.
So right now we are gonna have a small task for you. And after that, you're gonna have a lunch. But right now, so here you can see core. Please take your phones. Use your phones to make your answers for this final test. I suppose we'll give you nearly 20 minutes. Yes, it is a final. Only this one, yes, for the whole school. If it will be enough, 20 minutes. After that, you will gonna have lunch.